This conference will now be recorded.
Well, good evening. Welcome to tonight's webinar sponsored by the Northwest chapter of the Potomac Valley Radio Club. I'm Tom, K3AJ, filling in for Northwest chapter chair Jim, WX3B. Because we have a good program and we also expect participants from outside PVRC, we're going to dispense with the usual business and roundtable. Tonight, Donovan, W3LPL, will be presenting a talk on what to expect during the rising years of solar cycle 25. So I'll be muting all participants while Frank is speaking. If you have questions, please indicate that using the chat feature. You can click on the cartoon speech balloon at the top of the screen to get into the chat. We'll make sure that Frank addresses your question when he's ready to entertain them, and we'll probably do that at the end. You don't have to type in the full question. You can just indicate you have a question, and then I'll sort that out when we get to that part of the program. Participants should be aware that tonight's webinar is being recorded. Frank, W3LPL, probably does not need much introduction to many here tonight, but for those who may not know all about Frank, he has a long and storied history in amateur radio. He likes to say that he got his start back in 1922 when his grandfather began building one-tube radios. That knowledge and some of the materials even were saved all those years until Frank came of age in the 1950s, when Frank and his grandfather began building radios together. Frank moved through the familiar path of SWLing to earning his novice license in 1959 as KN1LPL. In his early days involved operating from an urban environment with the limited equipment and antennas that so many of us know about that were typical of those days for beginners. His interest in contesting was born during Field Day in 1959. Since then, Frank has gone on to build and lead a world-class multi station at his home in Glenwood, Maryland, notching many victories in this highest echelon of radio sport. Frank was inducted into the CQ Contest Hall of Fame in 1999. But there's more to Frank than winning contests. He's made a deep study of radio propagation and has a passion for understanding all of its aspects and, moreover, translating that knowledge in a way that others can understand and use, as we are about to experience. Frank? Got to unmute yourself, Frank.
Okay, good. So you hear me now, Tom?
Yes, you're good.
Okay, and thank you for that very nice introduction, and nice to see everybody on here tonight. We're going to try to go through my slides in about an hour's time. I know most of you are experienced hams, so many of these slides I will not read. The slides will be available after the fact. Either, I don't know if Tom can post them somewhere, but if not, you can always send me an email and request a copy of the slides. My email address has been on QRZ unchanged for the last 25 years, so it's not a problem to figure out how to contact me. And if you should come up with any questions that I can't address or don't address thoroughly tonight, you can always address an email to me and I'll respond. Okay, so these two images on the screen are kind of characteristic of the sun at solar minimum and solar maximum. The left-hand side shows the coronal holes that are so prominent during the solar minimum years, and we're still suffering with those somewhat today. As you'll see later in the presentation, those are the primary cause of the brief minor geomagnetic storms that we experienced near solar minimum, and we're still experiencing them to some degree today. And on the right-hand side is the more active sun that we hopefully get to experience before too long. Okay. Well, for some reason, my page up, page down function isn't working as it normally does. Okay, I don't know what happened there, but anyway, there we go. There we go. Okay, so I think we're all right now. So solar maximum improves propagation primarily on the higher bands, 30 meters and above. It has very little effect on 40 and actually degrades 160 and 80 meters, especially 160. And I'll discuss that in some detail a little bit later. And there are much more frequent geomagnetically disturbed days during solar maximum, especially the more severe disturbances, which fortunately are not as bad. But there's another good aspect of it too, and that is, although we'll get many minor geomagnetic storms for higher up in the cycle, the increased solar flux tends to negate the effect of minor geomagnetic storms, so we can kind of ignore them. They don't have the effect of significantly depressing the MUF the way they do during solar minimum. And this is kind of a look at what sunspots are all about. The upper left-hand side is an image of one of the largest sunspots ever seen compared to the size of the Earth in that little image. And on the upper right-hand corner is a fairly recent video clip of a sunspot and its surrounding active region. That black area is highly visible. The big sunspots are actually visible with the naked eye. I don't suggest that anyone actually do that, but sometimes you can't help but notice it when they're so large. But the beneficial and degrading radiation that comes from sunspots actually doesn't come from that black region at all. It comes from that very active area surrounding it that you can see. And in the lower left-hand corner is a short video clip that shows the progression of a sunspot group across the face of the sun. This video probably lasts 2 or 3 days. So the active regions surrounding and above sunspots radiate ionizing radiation that's at the ultraviolet wavelength. That's the beneficial radiation for the most part. It also radiates X-rays, which can be a problem, which I'll discuss later. And then there's the negative aspects, which is the highly energetic plasma and the hard X-rays from solar flares that cause complete HF blackouts for an hour or two. So good news, the last sunspot for the last cycle was July 4th, 2020. It's been so long now since we've seen a sunspot from the last cycle that nobody's actually expecting to see any anymore. But the big unknown question, and I'm sure the one everybody looking at this presentation would like to have the answer to, is what's sunspot cycle 25 going to do? And I hate to disappoint you, but I don't care for this folly of getting involved in sunspot forecasting. I don't have the skills or experience to do it, but I do know that a very, very high percentage of those people who've tried to do it have wound up making fools of themselves, and I don't care to join their company. But I'll explain the phenomena we're going to see, and I'll voice a few opinions on some forecasts. So what's going on now? This is one of the reasons that I'm a bit skeptical of some of the forecasts. You know, you can pick any forecast you want. Just pick what you want to see for a solar cycle in the next 3 years or 4 years. Just pick a number you want to see, and you can find a forecast that matches it. Everything from a Maunder minimum with no sunspots at all the way to a record-breaking solar cycle that is even stronger than we had during solar cycle 19 in 1957 to early 1959, and anything in between. So pick what you like. But here's shown on this chart are all of the solar cycles since solar cycle 1, and their sunspot number shown on the vertical axis, and that big dashed green line is solar cycle 19, which was going on when I first got involved in shortwave listening. And that very dark black line in the lower left-hand corner is the progress of solar cycle 25 since solar minimum. And you can see that so far, the progress of solar cycle 25 much more resembles weak solar cycles than it does strong ones. but we don't know that those statistics will prove to be the case. But I'll tell you, if it gets to be, if anyone's read my May QST article, if we get to the end of the year and we're still seeing this relatively low solar activity, then we're almost certain to be heading for a solar cycle no stronger than the last one. And here's an expansion of that same chart we just looked at. And you can, and this chart goes through October of last year. It uses the smooth sunspot number, and the last smooth number available was from last October. So if you look at where we were last October, we were tracking the 3 weakest solar cycles on record. But if you look at that blue line there, that was a fairly strong cycle. So it's possible that the solar cycle we're in right now could follow the track of that blue line, or the dot dashed line below it. We just don't know yet. But by December, we're going to have a better idea. But there's no reason to believe. You look at all those solar cycles to the upper left-hand corner there, and 23 out of the 25 solar cycles are to the left of the black line, and 2 of them are to the right. So what about the higher sunspot number? Well, higher sunspot numbers have a very significant beneficial effect on the F2 region and the F region at night also. But the sun doesn't ionize the F region, and I'll explain the difference between the F and the F2 region later in the presentation. The F2 region faces the sun, so that gets ionized by the sun. The F region is at night, and it's the residual ionization that occurred during the previous day. Higher sunspot numbers have the greatest beneficial effect from October through May. The benefit is that all the bands 17 through 10 meters are significantly improved during the daylight and evening hours, not so much during the middle of the night. There are a few exceptions to that, but for the most part, it's daylight and evening. And 30 and 20 meters are significantly improved during the night throughout the year. For those who've been active in recent years, you know that 20 meters usually goes pretty dead at night during the winter. It's still quite active in the summer, but that's more a result of the summer solstice than it is sunspots. And 30 meters also goes very dead in the winter, and with more sunspots, it should stay open the whole night long. But along with the higher sunspot numbers, also we get many more, anywhere from minor to extremely severe disturbances, both geomagnetic storms and something called a sudden ionospheric disturbance, which I will explain a little bit later. So there are 2 daytime layers, especially in the summer, and we experience this right now. The F2 region is the only region in the ionosphere that supports 24-hour long-distance propagation. It's actually renamed the F region at night, but it's the same ionized area. In the daytime, the region that refracts our radio signals is known as the F2 region, and in the summer there's another region, primarily in the summer, called the F1 region that I'll describe later. So the F2 ionization is always greatest during the day, and it's significantly weaker at night, and it's renamed the F region at night. It's lower altitude, but during the higher sunspot cycle, there'll be so much ionization during the day that the residual nighttime ionization will be still quite adequate to keep 20 meters open all night long, just like it is in the summer, even right now. And the amount of F2 ionization varies very greatly, and we all know about the variation during the day. You know, we're all kind of used to the higher bands opening around sunrise or shortly after, and there's a big seasonal change, especially between the summer and the winter. And geomagnetic storms have a big effect on the amount of electron density in the F2 region and at night in the F region. And those have the primary effect of reducing the maximum usable frequency. And the 4 phases of the solar cycle also affect the F2 ionization. Everyone's familiar with solar minimum. We've thankfully departed that phase of the solar cycle. We are now in the rising phase of the solar cycle. Normally that lasts about 3 years. Let's do a little computation here. We're 18 months after solar minimum, and we're not seeing a whole lot of activity from the new cycle. So we've got about 18 months to go before this is either a weak cycle or a solar cycle with a very unusually long climb to solar maximum. So the 3rd phase is solar maximum. That usually lasts about 4 years. And then there's the declining phase. The declining phase, of course, there's less F2 ionization, and there's also still quite a bit of geomagnetic instability during the declining phase. I'll also mention that the first year or 18 months of the rising phase that we're in right now is typically the quietest time of the solar cycle. And I think that's kind of what we've experienced. There have been very few geomagnetic storms or active periods during the last 18 months, but that's going to change, and it's going to change very quickly. And if it doesn't change, that's another troubling indicator of a quieter than expected solar cycle 25, because the increased MUF from increased ionization goes hand in glove with the increased geomagnetic activity and disturbances. They go hand in glove, and you can't have one without the other. And those are the 4 cycles of the 4 phases of the solar cycle I just mentioned. And here's a look, kind of, this is I think this kind of a question appears at the general class exam as to what the regions are. The daytime regions are the F2 region, which is very high altitude, about 400 kilometers. And then there's the F1 region, which is an area that primarily degrades 20-meter propagation during the day in the summer. Some hams mistakenly refer to that as absorption, but it's not, and I'll discuss that later. The E region, which most hams who operate 40 meters in the day encounter this region. It's the region that's responsible for the normal routine 40-meter propagation that covers out to 400 or 500, 600 miles. It's also host for the sporadic E propagation that we get to enjoy in June and July, and it can be a lot of fun. Sporadic E is not affected very much by the solar cycle, so I won't discuss that very much at all. It's affected very strongly by the seasons, and it occurs every single day during June and July, and then it fades away pretty quickly by the middle of August. And the D region is an absorbing region, and it's there only during the daytime. At night, the ionosphere has only one region, and that's the F region. And there's an error on this slide. The actual altitude of the F region is lower than the F2 region. It's down at about 300 kilometers. So the F1 region appears essentially every day during the summer. And anybody who operates 20 meters in field day, for example, knows that during the daytime you work mostly short distance stuff east of the Mississippi. And it isn't until late in the afternoon or early evening that 20 meters opens up to the West Coast. And that is not absorption. It's a phenomenon called blanketing. What is blanketing? It simply means that the F1 region is refracting signals that we would prefer would penetrate the F1 region and refract from the F2 region. But the F1 region MUF is a little bit above 20 meters in the summertime, so during the day, low angle radiation that we would prefer to use for DX instead bounces off the F1 region and winds up in Indiana or Nova Scotia instead of halfway around the world like we'd like to do. and like we do in the winter. Okay, and the E region, the region that is active on 40 meters every single day of the year, is also a blanketing region. And hams mistakenly refer to late afternoon. I don't know what that was, but hams mistakenly refer to late afternoon propagation on 40 being hindered by. I think somebody's not muted. And that's not the problem at all. It's not absorption, and any thought that there is an absorption issue late in the afternoon that is preventing the bands from opening for DX is not true. It's blanketing again, but in the case of 40 meters, it's blanketing by the E region. So what's happening is that low angle radiation that we would prefer would go straight up to the F2 region. Instead, it encounters the E region and gets returned to Earth in northern Maine or Nova Scotia instead of in the middle of the Atlantic Ocean as it's on its way to Europe. So it's blanketing, not absorption. So after sunset, the F1 region combines with the F2 region, as I mentioned earlier, producing a lower altitude but still densely ionized nighttime region. During solar minimum, the MUF drops below 20 meters during the winter, also drops below 30 meters during the winter. So during solar minimum, 40 meters is kind of the highest frequency band that we can use, but it's quite good. Okay, so I think I've discussed that. So what is this all about? This is a physical display of a lot of the phenomena that affect propagation. So let me take a minute to explain this. This is something called an ionogram, and in particular, it's called an oblique ionogram. Well, what does that mean? Most ionograms are taken at zenith angles, straight up. So the way they're done, the traditional ionograms at zenith is that the transmitter and its associated antenna send a signal straight up, and then it's reflected off of various layers of the ionosphere, and they come back to a co-located receiver. Well, that's not what this is. This is a transmitter that is located about 2,000 kilometers away from the receiver. And of course, we have GPS now, so it's very easy to synchronize a transmitter and a receiver with very great precision. And that's what this is all about. It's a pulse transmitter. And if you listen on the CW bands, you hear these things, or on the sideband bands, so they go sweeping past the narrow channel we're listening to. So in this particular display, the vertical axis is time delay. So that creates perhaps a slightly counterintuitive display. And the axis from left to right is frequency. And I've highlighted the main frequencies of interest to us in the upper part of the display, starting at 10 megahertz, going all the way up to 10 meters. So let's take a look at some of the physical measurements. And by the way, I looked through a whole series of these displays and picked one of the ones that's most easy to interpret. Normally, these things are a real bear to interpret visually, and unless you look at these things very frequently, they're really a nightmare to interpret. But this one was a very clean one, so that's the one I'm showing here. So let's look at some of the primary attributes that it's showing. This ionogram was taken in the morning during the fall. So you can see that the shortest time delay, so the first line shown at the bottom of this display is a 1 hop off the E region. And by the way, the intensity of the received signal corresponds to the brightness of the display. So you can see that when this particular ionogram was taken, the E region was pretty active up to even up to about 18 megahertz, and then it faded off. And the next region that was encountered during this ionogram was the 1-hop F2. And you can see here, looking at the bright part, that on this particular propagation path, the strongest intensity is in the lower right-hand corner from about 20 megahertz through about 28 megahertz. And it was also pretty good below that, but significantly stronger at the high end. And there's another interesting phenomenon that's clearly visible in this particular ionogram. I am not going to explain this in detail, but for those of you who are interested in this, it's called a Peterson ray. And what it is, at the higher end of the propagation path, the signal can arrive by two paths via 1-hop F2. One is a low angle path, that's where that really bright part of the display is. And then if you go up a little bit higher, you can see there's another path there, and the signals are not as strong. And that's a high angle path, so it has a longer delay. And these two paths are fairly commonly present on the 12 and 10 meter bands, and it causes fading. And the only other things I'll mention here are some of the 2 and 3-hop paths, and recalling that this display is strictly time delay. So you can see the 2-hop E path kind of fades away just above 10 megahertz. It's strongest around probably around 8 or 9 megahertz. The 2-hop F region is much stronger on 20 meters than the 1-hop for this particular path. Notice the trace is much brighter on 2-hop F than it is for the 1-hop F at 14 megahertz during the day on this particular day. And then if we go up to a 3-hop path, it looks like at about 10 megahertz it had about the same strength as the 2-hop, and the 1-hop F2 path was very weak at 10 megahertz. So this is a physical instantiation of a lot of the features of the ionosphere that we speak about. So, as I mentioned at the very beginning, the primary effect of the increased solar cycle is on the F2 region. So that's the beneficial propagation, but it affects other things as well. And this shows for the D region, which is the absorbing region that's present during the daytime, especially degrades 80 meter propagation, and it really degrades 160 propagation during the day. You can see during solar minimum that the amount of absorption from the D region is about the same for every solar cycle. It doesn't matter very much whether the previous cycle was a strong one or a weak one, but the amount of absorption is greater during the stronger cycles, but it's only greater by about 25%. So it's not like the F2 region where the MUF doubles or triples during strong solar cycles. In the case of absorption in the D region, the absorption increases only by about 25%, and compared to weaker cycles, and it's less than twice, even for the strongest cycles. The absorption at solar maximum is less than twice the amount of absorption at solar minimum. So this isn't as big a deal. So we're going to see more severe E region blanketing. So 40 meters, the primary effect here is that 40 meters won't open for dxing until later in the afternoon. The E region blanketing will persist longer, but eventually the E region will fade away, and 40 meters will be as good as it ever was once that goes away. On the case of 80 meters, the residual E region during solar maximum can persist even after sunset. So there'll be some days that are pretty good at sunset, and some days where we have to wait a little bit longer. And on 160 meters, unfortunately, the residual E region ionization can last many hours after sunset. Some days it won't, some days it will. It's not predictable, except that it's more of a problem during solar maximum than it is during solar minimum. And this is the biggest effect on the low bands, is the degradation of 160 meters during solar maximum. Okay, so those who observe propagation phenomena are probably aware that there's a tendency for propagation to vary on about a 27-day period. And what's going on there is that our star, the sun, is a gas star, like they all are, and they rotate at a varying speed. It's a slower rotation at the solar equator, it's about a 25-day rotation, and it's about a 35-day rotation way up near the pole. Well, most, in fact, virtually all of the propagation-related effects from the sun occur at the relatively low solar latitudes. And many of them are up at that region marked as 27 days. So the nominal repetition of beneficial propagation from sunspots, many of them will repeat a second time around and even a third time in some cases. And also the negative effects of geomagnetic storms tend to repeat on a 27-day cycle. So if you're getting prepared for a contest, for example, it's helpful to take a look on the bands 27 days before, because there's a pretty good chance, not a guarantee, but a pretty good chance that things will repeat after 27 days, and this is why. I'm going to just briefly talk about a fascinating type of propagation that affects the 6-meter band, and it's called transequatorial propagation. This same propagation is present on 10 meters, but it provides us with somewhat more reliable propagation into Argentina, and that's kind of a routine thing on 10 meters anyway. So, but the big excitement from this mode of propagation is on 6 meters. And it's very counterintuitive as to how it actually works. One would think, if you haven't studied propagation, that the maximum ionization would occur at the equator, but it doesn't. It's not that simple. There's a major interaction between the ionosphere and the Earth's geomagnetic field near the equator, and that causes the peak ionization during the day to occur in 2 places. And those places are about 1,000 miles north and south of the geomagnetic equator. And where is that? Well, for us in the eastern part of North America, this propagation primarily on 6 meters gives us sort of a pipeline into Buenos Aires when this propagation is available to us. Now, the TEP mode, it's one of its great benefits is that it can propagate about 5,000 miles without an intermediate ground reflection. So its efficiency is very high, and the MUFs of these 2 ionization crests are higher than the normal F2 region MUFs. So you get a double benefit of higher than the normal ionization and less loss, because we avoid a lossy ground reflection. So the propagation on this mode is typically from Haiti to Buenos Aires. Well, why are you bothering me with this? We live in the United States. Well, on 6 meters, sporadic E propagation is pretty common. Anybody who's on the air in June and July knows about it. It's there every day. It might not be in the place we want it to be, but there's always sporadic E every day in June and July. Unfortunately, this TEP mode is very weak in June and July. And the reason is that only one of these crests has high MUF, and the other crest is in the winter season, and its MUF is depressed. So this is a very poor mode of propagation in June and July. But in especially April and the early part of May, there is still some sporadic E. So from us in North America, on those days when we get a sporadic E hop, let's say from Baltimore to Haiti, that's a pretty reliable one hop sporadic E path. So on those days when that path is present in April and May, we can couple into this very strong TEP propagation, and we can work as many stations in Argentina as we'd like, and also the surrounding countries, Chile. And even if there's a little bit of sporadic E, it can work into the Falkland Islands and other places around there. So this is a fascinating mode of propagation. It's really efficient. I remember once working about 8 years ago, a ham in Buenos Aires, and received a QSL card from him showing his station, and it was a Yaesu FT817 on his patio table at ground level, and above directly above the FT817 was a one element quad loop. And he worked me with that quad loop on one of these TEP days. It's amazing. And it's a lot of fun. Magic band, 6 meters. But that's the end of my comments about 6 meters for this presentation. The bands that are primarily improved by the new solar cycle are the high bands. So we'll start to just take a quick look at what we might expect if we get a good, strong new solar cycle. Even a weak solar cycle will produce occasional very good days, but a strong solar cycle, we had solar cycle 24, the last one was a fairly weak one. The three cycles before that were pretty strong. And what we experienced during those fairly strong cycles was long path openings, particularly in the spring and the fall, to Southeast Asia and Japan in the morning. So hopefully we'll get to enjoy that again. It usually happens around 1300 Zulu. And in the late afternoon, we even get occasional sporadic E openings to Scandinavia. This is often a big surprise to him. So, the 10-meter band opening to Europe ended. And then if they're paying attention, all of a sudden, there's these big, strong Scandinavian signals. And that's usually about 3 o'clock in the afternoon. And it's sporadic E in the polar region. And it's pretty common. And because it's sporadic E, the MUF can be high. So if a station in Finland calls you on 15 meters, it's highly probable that if you ask him to go to 10 meters, that he'll be just as strong there. 15-meter propagation is pretty reliable even during weak solar maximums. So we're likely to get some pretty good European openings, even JA openings, but they'll be briefer than we'd like, even if we have another weak solar cycle like the last one. And these occasional openings to Scandinavia late in the afternoon are even more common on 15 than they are on 10. Let's just take a quick look at the mechanism of long path. Long path tends to exist in the vicinity of the day-night terminator. So this is a look at what long path looks like between the northeastern US and Japan. And this is the long path that we notice most often, simply because there's a very big ham population in Japan. This same long path type propagation occurs at our sunrise, but the other end of that path is over South Asia and the far eastern part of the Mideast, and there's not as much ham activity there. So it's a little more difficult to notice it, but the same path is still there. And on the higher bands, the path is probably a little bit more on the daylight side of the daylight darkness terminator, and on the low bands, the propagation path is probably a little more on the darkness side of this terminator. So the primary effect of the improved sunspot cycle on 20 meters is nighttime propagation year round. So if we get a decent solar cycle, we could expect 20 meters to be open essentially all night long, 12 months out of the year. It's been a long time since we've experienced that, but it should come back. The nighttime propagation we're experiencing now pretty reliable right now. 20 is open to Europe almost all night long right now, but that has nothing to do with the solar cycle. It's all about the amount of radiation that's impinging on the polar region. It's always daylight up there. This the midnight sun, and it affects propagation in a big way, even without lots of sunspots. During the middle of the day, the F1 region is active essentially every day during the summer, during the high sunspot cycles as well as the weaker ones. And this is a blanketing region that causes 20 meters to be not a DX band during the middle of the day in the summer. And anyone who's been on a D expedition down in the lower latitude regions has experienced this even in the fall and the spring, where 20 meters gets to be just about dead for dxing, and it's caused by, not by absorption, which a lot of hams mistakenly refer to it as. It's caused by F1 region blanketing, or simply F1 region low angle propagation to places we don't care about. So what band should be using for dxing during the next 2 years of the rising phase of the sunspot cycle? Well, each band has its own unique advantages and disadvantages. At this part of the solar cycle, 20 and 17 meters are the go-to bands for DXers, and increasingly 15 meters, especially hopefully this fall and through the winter. The most reliable nighttime band during this rising phase of the solar cycle will continue to be 40 meters throughout the year. And 20 meters should have improving nighttime propagation, especially in the spring and early summer, but probably not so much in the winter until we get a little higher into the sunspot cycle. And early in the rising phase, where we are now about halfway through the rising phase of the solar cycle, 80 meters is still a pretty good band. The E region blanketing isn't yet a big issue, but of course the noise level on 80 and especially 160 can be pretty onerous during the summer. Most of us don't spend a lot of time on 160 in the summertime. So I think I've covered most of this during my comments, so I'm just going to skip over this slide. I don't see anything here I haven't already discussed. So this is another version of an ionogram that I showed you earlier, but this version has been processed by a computer to make the data a little more useful and more easily interpreted by an untrained human observer. So this again is showing us a lot of these phenomena that I've discussed. So this computer display on the vertical axis, it's elevation angle in degrees. So that's the radiation angle from your antenna. So the computer has changed the time delay and reprocessed the data so it represents angle of elevation off an antenna. And just like in the previous unprocessed display, the horizontal axis is distance in kilometers. So in this particular ionogram was taken on 20 meters at local noon during the summer. So this is classic noontime field day. So what's going on? For antennas that are radiating at low angles of radiation from 0 to 20 degrees, those are the antennas we normally consider to be great dxing antennas. Well, in the summer, it ain't so. That low angle propagation is intercepted by the E region, which prevents those signals from getting up to the F2 region where we want them to go. And it provides, the E region provides us propagation out to about 1,000 kilometers or so. And then once our signals finally break through the E region at higher angles from 19 to 25 degrees in this particular case, it hits the F1 region and still prevents us from getting very far. It's about 1,500 miles on this particular day. And then finally, with radiation angles above about 20 degrees, 25 degrees, our signals finally get to the F2 region. But unfortunately, because the angles of radiation are so high, that even the F2 region only propagates the distances out to 1,000 or 1,500 kilometers during the middle of the day. And in this particular day, when the radiation angle from the antenna was above 56 degrees, the signal propagated through the ionosphere and out into space. So 20-meter daytime field day is short distance propagation. It's very similar to 40 meters. So I've already talked about this blanketing phenomenon, so I'm not going to go through step by step of all this reading. These slides will be available to you after the presentation. And I've already talked about degraded 40-meter propagation. The D region doesn't play as big a role in propagation. The amount of absorption from the D region decreases with the square of frequency. It's not linear. So as you go up in frequency, the amount of absorption decreases with the square of frequency. So the amount of absorption at 7 megahertz is 4 times less than it is at 3.5 megahertz. And at 30 megahertz band, the 30-meter band, the absorption is about 5 or 6 times less than it is on 80 meters. So the D region isn't as big a deal as it is on 80 and 160. The big deal is the E region. And here we can see an actual physical realization of these concepts. The same kind of display I showed for 20 meters, but this is 40 meters in the middle of the day in the summer. So this is field day. And you can see in this case, antennas radiating up to about 40 degrees elevation angle. They intercept the E region during the middle of the day, and propagation extends out to about 600 kilometers or less. And then for the higher radiation angles from 40 to 60 degrees, the F1 region blankets the F2 region, so we can't get to that region. And we're still only propagating out to, at best, 600 kilometers for relatively high elevation angles from our antenna. And then finally, when we radiate from our antenna almost straight up, propagation known as near vertical incidence skywave, NVIS, we're really talking about short range propagation out to 400 kilometers or less. So this is field day on 40 meters. Well, we all know it's a short distance band, and there isn't anything you can do to prevent that. It covers out to about 600 kilometers, no matter how high or how low your antenna is. 80 meters is degraded during the higher solar cycle. It's mostly caused by D region absorption during the late afternoon. And then after sunset, residual E region ionization will still cause some blanketing on some days, not every day. And the effect of E region blanketing is least during the middle of the winter. So for example, that E region blanketing can be a pretty significant effect on 80 meters in the CQ Worldwide contest in October, but usually by the CQ Worldwide contest in November, that E region blanketing after sunset is no longer a factor, usually. At 160, well, it really suffers at the top of the solar cycle. There's just not much you can do about it. Late in the afternoon up until sunset, 160 is pretty hopeless. And then after sunset, the E region blanketing can persist for many hours after sunset, making propagation really inefficient, extremely inefficient on many days. About the only way we avoid this is by focusing our 160 activity at solar maximum during the period from the middle of November until the end of February, when these E region blanketing problems are reduced. Okay, so most of my discussion here has been about ionospheric propagation, the good kind and the bad kind. The good kind off of the F2 layer, and the bad kind being blanketing from the F1 and the region during the summer, and the E region all year round. The rest of the presentation deals with the other stuff that comes along with the increased solar activity. On the left, the illustration on the left side is what the sun looks like during the years near solar minimum. And it's dominated by this thing called a coronal hole. And it's one of the largest features in the solar system. You can see that dark region extends from the northern polar region of the sun almost all the way to the southern polar region. It's a huge feature. And it's an area where the magnetic field lines from the sun extend out into deep space. And it allows charged particles from the sun to escape into space and cause us all kinds of problems. The good news is that the increased ionization at solar maximum tends to wipe out most of the negative effects of weak solar storms. So the minor storms that have been plaguing us for the last 5 or 6 years, although they will continue, the increased ionization tends to offset the degradation from minor storms from coronal holes. So we can ignore this illustration on the left side because it won't be that significant anymore. The whole coronal holes will still be there, but the increased solar ionization of the F region tends to offset it. But on the right-hand side is something we haven't seen much of. And this is an illustration of something called a coronal mass ejection. These are areas that tend to be located near sunspots, and they are explosions of billions of tons of charged solar particles, creating huge clouds of particles extending out into space. And these clouds of particles are so large that if the explosion of the CME from the sun is on the part of the sun that faces the Earth, as opposed to the backside of the sun, there's a very good probability that at least part of that cloud of charged particles will intercept the Earth. So I think I've said most of what I have written down here. You can read those words later if you care to look at the slides, but the key point is that coronal mass ejections are the big deal that's going to affect us in a negative way over the next 6 or 7 years. And I think I've already said everything I wanted to say about this. These coronal mass ejections, if anyone follows my daily propagation article in the Daily DX or on the PVRC email reflector, these reports of coronal mass ejections are getting to be more frequent. They're relatively weak, but they will become very, very common and much stronger over the upcoming years. So what's going on with these coronal holes? They create high-speed streams of charged particles, and their effect gets magnified as the coronal hole high-speed stream travels from the sun into planetary space. And well, how can that be? How can these streams get worse after they leave the sun? Well, what happens is the ambient solar wind is dense, but it's slow compared to the high-speed solar wind. It typically is about 300 or 400 kilometers per second. Doesn't seem very slow, but compared to the high-speed coronal hole streams, it's about half as much or 1/3 as much. So the coronal hole high-speed streams are about twice as fast. And what happens is when one of these coronal hole streams erupts from those open areas, is they catch up to the slow speed. So it's, if you can imagine that that you're in a very high-speed speedboat, and if you look at the front of that speedboat, you can see that there is a bow shock in front of the speedboat, and that's exactly what's happening in the solar wind. This high-speed stream is colliding with the slower ambient wind, and it produces an area of compressed solar wind shown in red here. And that's what causes, it's actually what causes these geomagnetic storms. They're weak and they're short-lived. It's that area of compressed solar wind rather than the high-speed stream itself. So this is just another illustration of that coronal hole high-speed stream as it leaves the sun. But the real effects happen in the solar wind from the collision with the slow solar wind. By the way, the slow solar wind is always there, and nobody knows what causes it. It's very dense, and you can win a Nobel Prize if you can prove what causes it. But it's always present, about 300 to 400 kilometers per second, billions of tons per hour of radiation. Don't worry, the sun's not going to go away. The sun has been radiating billions of tons of matter for billions of years, and maybe we'll have a problem in about 3 billion years, but until then, we're okay. So these coronal mass ejections get to be much more frequent. So unlike the storms we've had for the last 5 years, which typically last 3 hours or less, some of these moderate to severe storms are going to last much longer. They are the dominant cause of the strong and severe storms. This is a look at an image of how large these clouds are. So the chances of intercepting the Earth are pretty darn good when one of these occurs on the Earth-facing side of the sun. So what about the strength of these storms over time? Coronal mass ejections occur quite infrequently during solar minimum, and they tend to be weak. And of course, not all of them affect the Earth. So during solar minimum, we tend to get weak CMEs that we don't worry about hardly at all. But as we climb the solar cycle, you can see from this graphic that the number of CMEs is increasing, so that we're typically seeing 1 or more a day already. And when we get to solar maximum, we'll see 5 or 6 CMEs per day. That doesn't mean 5 or 6 CMEs will intercept the Earth, but that many CMEs will be ejected from the sun. So 10 times as many roughly during solar max. So this is a very complex slide, but it's the most important slide in the entire presentation. So I'm going to take a couple of minutes to explain it. And you can take a look at this afterwards. It truly is the most important slide, and when you understand this, you have a better idea what's going on with disturbed geomagnetic conditions between solar minimum and solar max. So the pie charts in the upper half of this slide represent solar minimum and the years near solar minimum, so roughly the last 5 years. And the pie charts at the bottom half of the slide show the changes that occur during solar maximum for these disturbed conditions. So let's look at some of the main features of this chart during solar minimum, where we've been for the last, seems like forever. It's been about 5 years. So you remember we talked about coronal hole high-speed streams. These are these interaction regions in the solar wind caused by the high-speed streams intercepting the slow solar wind. And if you look, almost all, 2/3, I guess, of the disturbed conditions during solar minimum are minor storms. They last for 3 hours or less, and you can see on the pie chart in the upper left-hand corner that almost all of those are caused by coronal hole high-speed streams interacting with the slow solar wind. And during the solar minimum years, the strong and severe storms are relatively infrequent compared to the minor ones. These numbers, by the way, are the number of occurrences of minor, moderate, strong, and severe storms during a typical solar cycle. So you can see that coronal hole high-speed streams have a big effect during solar minimum, and fast CMEs have hardly any effect at all, other than the occasional strong and rare severe storms during solar minimum. But let's go to the bottom half of this chart, and you can see that the whole situation changes That's near solar maximum. The minor geomagnetic storms, they occur just about as often, but they're relatively unimportant because the MUF depressions that are caused by minor storms are pretty much washed out by the increasing MUF caused by the beneficial radiation from the sun. So during solar max, we can kind of forget about minor storms, even though they continue to occur, and they continue to be caused in part by coronal whole high-speed streams interactions with the solar wind and by fast CMEs. But look how much more frequently we get moderate storms, strong storms, and severe storms. And I'll talk a little about the statistics about those in upcoming presentations. So these fast CMEs, which are the CMEs that are fast enough to escape the sun's gravity, they're the ones that cause grief for us. So we get used to solar max of having very good days and some very bad days. Unlike solar minimum, we have, seems like, almost all very bad days. Of course, that's not really true. But there's a tremendous amount of variability during solar maximum. A fact that most hams are unaware of, but this is very observable, and that is a necessary precondition to strong to severe magnetic storms, and in fact almost all geomagnetic storms, is the orientation of the interplanetary magnetic field. What the heck is that? The solar wind carries charged particles. And whenever you have charged particles that are moving, that creates a magnetic field. And that magnetic field connects the Earth and the sun. So the Earth is very much part of the sun's magnetic field. And that field has about a 50% probability of being oriented northward or southward. So about half the time, more or less, it's oriented towards the south. Well, the Earth's magnetic field is oriented northward. And anyone who remembers the experiments we did in elementary school with horseshoe magnets knows that when the two magnets are oriented in the same direction, that the magnetic forces force the magnets apart. And that's what happens when the interplanetary magnetic field is oriented the same as the Earth's magnetic field. All of these particles get pushed away from the Earth. But on those days when the interplanetary magnetic field is oriented roughly opposite from the Earth's magnetic field, exactly the opposite happens. And a phenomenon called magnetic reconnection occurs, which causes the particles emitted from the sun to get trapped into the Earth's magnetosphere and cause havoc. That havoc we know of as geomagnetic storms. And these are the moderate, strong, and severe storms that we'll get to be used to during the solar maximum. If you want to learn more about magnetic reconnection, you can look it up on Google and learn as much about it as you care. The only important thing you need to know is that it's a necessary precondition to strong geomagnetic storms. This is reported on many websites as a parameter known as negative BZ, and I'll explain that in a moment. Okay, oh, and another interesting feature of geomagnetic storms, and I'll show the statistics in a moment, is that geomagnetic storms are much more frequent during the equinox seasons than they are during the solstice season. So during June and July, their geomagnetic storms are less frequent and not as strong. But that doesn't mean you won't get some that are strong, but they're less frequent. K-index. Hams, I think, in most cases are used to this. This appears on the general class ham exam, so new hams have to be familiar with this. At least they have to memorize it. And the range of K-indices runs from 0 to 9. It's a quasi-logarithmic scale. Quasi only to make it a little bit easier to interpret without having to go to a calculator to figure out what it means. So indices from 0 to 3 are quiet conditions. And during solar maximum, even levels up to 4 are generally quite acceptable at solar maximum because of the increased MUFs caused by the beneficial radiation. And we have experienced very, very few days or hours when the K index is above 6 or not 6 to 9 over the last 5 years. It's going to start happening much more frequently if we have a strong solar cycle. So this is an illustration of the orientation of the interplanetary magnetic field. So let's explain. This is a 3-axis coordinate system.
Say it, little one.
The x-axis is the axis connecting the Earth to the sun. That has a fancy name called the ecliptic. That name doesn't matter. On this coordinate system, the x-axis is Earth to sun line. It has virtually no effect on propagation. The line perpendicular to that is the east-west line labeled BY, and that also has very little effect on propagation. But the axis that makes a big difference is annotated BZ, and sometimes people will refer to this as negative BZ. That's the southward oriented interplanetary magnetic field. That is the necessary precursor to geomagnetic storms. And illustrated here down below is the relative strength of the K index 528 and the strength of the magnetic field in the southward direction. By the way, I'm carefully not using the word south direction. It's southward, so it's orientation roughly plus or minus 30 degrees from direct south. But the real killer, and this is what really affects this very strong storms at solar maximum, is the period of time over which the interplanetary magnetic field happens to persist. And if it persists in that southward orientation, the necessary precursor to storms, if it persists for hours, then hold on to your hat, because we're going to have some really severe storms. And this is another illustration of another fascinating effect. Those of us who operate 6 meters get to enjoy auroral propagation more frequently during solar maximum. And those of us who enjoy seeing the aurora can occasionally see it even at mid-latitudes around the Baltimore area. But you have to be really lucky, because not only do you need to have a really strong geomagnetic storm, you also have to have a cloudless sky, and you also have to have a sky with no moon. So the chances in the middle Atlantic area of having a very strong storm and a cloudless sky and a moonless sky are not good. And I've seen the aurora exactly twice over the 50 years that I've lived in Maryland. That's not to suggest that the aurora hasn't happened more frequently. And you can't see the aurora during the summer season either. The nighttime is just too short, and so you won't see it in the summer either. It's mostly spring and fall. So what goes on here? There's another phenomenon called this, if you recall, the magnetic reconnection was the necessary precursor to geomagnetic storms. There's an even stronger version of that, and believe it or not, it happens on the night side of the Earth. So if we look through this sequential illustration of what's going on when a coronal mass ejection hits the Earth, first of all, if the orientation of the magnetic field is southwards, then this phenomenon called magnetic reconnection occurs. What happens there is that the energy in the magnetic field gets converted to kinetic energy and speeds up it accelerates the charged particles that have hit the Earth. Now, they still get pushed around the Earth by the magnetosphere. If they didn't, we would get fried. So these charged particles still get pushed around the Earth, but as they extend beyond the Earth to the far end, and that's an area that has a name, kind of an unusual name, it's called the magnetotail. And that's the area where these charged particles reconnect. Another magnetic reconnection event, even more powerful than the one on the sun side of the Earth. And when this reconnection occurs, the magnetic field, and by the way, this is now also not only the solar magnetic field, but also the Earth's magnetic field, which is dragged around during one of these severe storms. When that reconnection event occurs on the far side of the Earth, the magnetic energy gets again converted to kinetic energy, which causes these particles that were dragged to the backside of the Earth to get accelerated towards the Earth. So most of them get accelerated towards the Earth or in the opposite direction to outer space. But we don't care about the outer direction, but what happens in the inner direction is illustrated by the 4, is at very high speed, these particles get accelerated back to the Earth. They hit the ionosphere and the atmosphere in the auroral region and create very brilliant auroral displays, typically after midnight. And if you want to observe the aurora, if you're lucky enough to see it, you really want to stay out and watch it for several hours, because these periods of magnetic reconnection tend to occur for brief intervals about an hour apart. And it's really spectacular if you happen to see one. And it improves the VHF propagation as well. Okay, so I'm not going to read this slide in detail, but the strength of storms is one of the ways to measure it is with the K-index. Minor geomagnetic storms, which correspond to K-index of 5, there's about 1,700 events per year on about 900. I'm sorry, per solar cycle, about 900 days per solar cycle. Of course, most of these occur during the 5 years near solar max, but they're not very important events. But the stronger geomagnetic storms, most of them occur during the 5 years near solar maximum. So you see these event counts that are shown here, 360 days a year for moderate KP of 6, and then the strong KP of 7, about 130 days. Almost all of those days are during the 5 years near solar max. And then thankfully, the very strong storms are very uncommon, about 60 days during the 5 years near solar max, so maybe a dozen days per year. And then the K-index of 9 corresponds to a severe storm. We didn't have any of those during the last solar cycle. And if we have another weak cycle, there's a very good chance we won't have any of those either. But doesn't mean we won't have any, the probability is lower. And if we can also plot the frequency of these storms during solar active years. And this chart shows the number of days per year with geomagnetic storms. And you can see during solar cycle 23, there were many more of these stronger storms in solar cycle 23 than we had during the last cycle. At least twice as many, perhaps 3 times as many. And if you look at the really strong ones, which are illustrated in red, you can see there's a lot more red in solar cycle 23 than there was during 24. There were only a couple of years that had these strong storms during the last cycle. So there's a very strong solar cycle dependence on these stormy periods. So if you want the really good benefits of a solar cycle, you're going to get a lot more frequent negative effects too. Another way to look at this is daily variability of geomagnetic disturbance. So let's look at a couple of the extremes of this chart. I'm not going to step through these one by one. So on any particular day during the course of an entire solar cycle, the chances that the K-index is going to remain at 0 for an entire day is pretty low. It's an 82% chance that the K-index will exceed 0 on any particular day. And if we get to higher numbers, like for example, the K index of 6, which is a moderate storm. They'll be fairly common in solar maximum. There's about a 5% chance on any particular day during solar maximum that we're going to experience these stronger storms. So I'll give you an idea as to how often it's going to happen. So maybe 1 or 2 days per month. And that tends to be concentrated during March and April and September and October. That's when we'll have these stronger storms. And the really, really strong ones, the probability of having those is small, but not zero. Another way to look at this is seasonal variability. There's a lot of detail in this chart. The most important thing to notice is that this is for geomagnetic disturbances, so the K index of 4, which is 1 step below a solar storm. There's about twice as many geomagnetically disturbed days, K index of 4 or greater, in March and April than there are in June and July. So right now, we're in the middle of June, we're at this very quiet time of the year. I refer to this as the quiet season, quiet geomagnetic season. And that activity will pick up again in September. And this is another way to view the same thing in a kind of a complicated chart. The only important thing about this chart is that the blue area is the low K indices, and the red area is the high K indices. And you can see very clearly in this presentation that the higher K indices are much more prominent during March, April, and early May than they are at this time of year during June and July. And there's also a variation with time of day. And one more way to look at this, so this is for geomagnetic storms. The other version of this chart was for disturbed days. So this is geomagnetic storms of 5 or greater. So these are moderate storms and stronger. And you can see this same distribution where the moderate to strong storms during the more active solar cycle years are much more common in March and April than they are in June and July. And the same applies to September and October. Much more likely to have very strong storms during those months. So let's look at the distribution of these phenomena over the map, over the United States. The southern border of the aurora is pushed southward by the solar wind. And I'm going to show you a photograph of the aurora that illustrates this very strongly. But the important thing about this is, first of all, to recognize that this is nighttime. The aurora has relatively little effect on propagation on the day-lit side of the Earth. But at night, the effects are magnified because the aurora is pushed southward. And on the most extreme storms, the aurora gets pushed all the way down to the mid-Atlantic states. This is a photograph of the aurora taken from a satellite over the North Pole. And this is actually multiple images that are spliced together, but you can see this very strong daylight versus darkness effect on the intensity of the aurora. The aurora is not very important on the daylit side of the Earth, but it's very intense, especially after midnight. And you can see on the midnight to sunrise part, which is on the lower right-hand quadrant, the effects of the magnetic reconnection on the darkness side of the Earth. And this is a fascinating photograph. It's actually 2 photographs that are spliced together rather crudely. This is the United States, but it's the United States as you've never seen it before. You can see all the cities. Florida is very clear here, but that white stripe across the northern part of the United States is the aurora at midnight on March 15th, 1989. Very, very strong geomagnetic storm. And in this photograph, you can clearly see how the aurora at night was pushed down to low latitudes. It was actually sitting up over Baltimore at the bottom edge there, and it was very wide. You can see how the width of the aurora grew as the night wore on. So on the left side towards California, the aurora was just starting to intensify. And then as we got towards the midnight area, towards the center and the right, the aurora was much more intense and much wider and much further south. And here's an illustration of that. The illustration is kind of disappointing compared to the vivid photograph of the aurora, but you can see the noon side of the aurora is very high in northern Canada, and it's relatively narrow and not very intense. And the midnight side of the Earth, the aurora, is further south. And this is on a relatively quiet night, so the auroral oval is not very strong at all. And it is centered on the geomagnetic pole, not the magnetic pole. So it's not that pole that we've read about drifting over towards Siberia, the one that affects our compass. This is the geomagnetic dipole, the northern pole, and it has only moved a few hundred miles over the last few centuries. So it's still over northern Canada, extreme northern Canada. So the aurora causes absorption, but that absorption only occurs significantly after midnight. That absorption is in the D region. That's the only part of the ionosphere that can cause significant absorption. On the daylit side of the Earth, that actually the normal absorption of the D region is stronger than the effects of the aurora. So the aurora, the main effects of the aurora are nighttime effects. We're going to get briefly into another type of disturbance. These are called sudden ionospheric disturbances. They're caused by very strong solar flares, which is another type of eruption from the active regions in the vicinity of sunspots. You will sometimes see, especially in the popular press, an incorrect description of solar flares, the effects lasting for days. It is not true. The effects of solar flares primarily from a ham radio point of view with propagation occur in very suddenly after X-rays leave the sun at the speed of light. They arrive on Earth very, very quickly, and the effects persist for an hour or two, and then the effects are gone. And what the popular press often refers to is the coronal mass ejection, which we've already talked about, which often occur coincidental with solar flares, but they're not caused by solar flares. And it's incorrect to state that because you've had a solar flare and the resultant ionospheric disturbance, and I'll describe that in a moment, it's incorrect to say that the CME was caused by the solar flare. It was coincidental with, and they're very commonly coincidental with flares, but they're not caused by them. And this is an illustration of how big these flares can be. The left side shows a solar prominence and its size compared to the size of the Earth. That doesn't mean that the Earth was at that location. It's just a comparison. And this on the right-hand side is an image of a very, very intense solar flare in 2003. These were both X-class flares, which are the ones that primarily affect propagation. And this illustrates the little video clip on the left-hand side shows one of the strongest flares ever recorded in 2003, and the four flares that occurred over those 3 days. There are also weaker flares, which are referred to as A-class, B-class, and C-class flares. They're very frequent, and they have no meaningful effect on HF propagation, so they're not even referred to on these slides. They're very common. They're of interest to scientists, but they have absolutely no effect on radio propagation. And you can see that just like for CMEs, these flares are much more common during very strong solar cycles than they are during weaker ones. During solar cycle 24, there were more than, this is the last solar cycle, there were more than 2,000 of the M-class flares. Most of those had minor effects on propagation, and less than 200 X-class flares, and most of those were the weaker X-class flares that caused sudden ionospheric disturbances. These sudden ionospheric disturbances can only occur in the daytime. They're caused by X-ray radiation from the sun, and that radiation cannot impinge on the dark side of the Earth. So if anyone tells you they experienced the sudden ionospheric disturbance during the night, they're mistaken. So let's take a look at the frequency of occurrence of these events. We care primarily about the very strong M5 or the M-class flares, so M4s and M5s. They occur about 300 days per solar cycle, but their effect is only a few minutes. So for the most part, we won't even notice them. It's the X-class flares that we will notice. The X1 class flares, about 140 days per solar cycle. They last about an hour, mostly affecting high latitude propagation. The ones that you hear hams talk about when they've experienced them are generally the X10 and stronger ones that affect propagation at mid latitudes, and their effects last for an hour or two. This is D region absorption, and the D region ionization declines very rapidly after the end of one of these events. So normally what will happen is that the X-ray radiation will very intensely ionize the D layer, and during an X10 class, we'll lose propagation on all of the bands up through 10 meters. But then over the next couple of hours, all the bands will come back just as if nothing had ever occurred. The 10-meter band recovers first, followed by 15, and then all the way down to 40 meters. And this is my last slide. This is what I use for propagation forecasting. I have relatively little use for the long-term propagation forecast you can get from computer programs. It turns out that the most important effect affecting propagation at the higher level of the solar cycle is this phenomenon called magnetic reconnection. It is dependent on the magnetic field being oriented southward. Well, if anybody thinks they can predict when the magnetic field of the interplanetary magnetic field is going to be oriented southward, if you think you can predict that, you should go ahead and reserve your hotel rooms for the Nobel Prize, because it will be awarded to you. No one has figured out how to predict the magnetic orientation of the IMF. It's one of the great mysteries of the solar system. Eventually, somebody will probably start to figure out some of the precursors, but at the moment it can't be done. So you might have the best software in the world to predict propagation, but there's a pretty good chance, 50% chance, that the IMF will be oriented southward, and all of that software will be useless. So I find much more useful is this new tool that's available to all of us on the reverse beacon network. And this shows actual propagation rather than forecasted propagation. That tends to be pretty good correlation between today's propagation and tomorrow's. So if you look at what's happening today, and if you have some familiarity with what might be different in terms of space weather tomorrow, you can have a pretty good guess as to what tomorrow's propagation will be as well. And this particular map was taken from the reverse beacon network, and you can see the exact web address at the bottom of the screen, beta.reversebeaconnet.net/main.php. If you go to that website, you can look at these maps for now. And And there's a set of radio buttons right below the map that allows you to select the bands. You can select more than one band if for some reason you want to do that. This particular map I drew in January of this year, and I selected the 80-meter band, so you can see that check mark. I selected CW. There's far more CW signals on the RBN than there are RIDI or PSK. So I checked that, and what I did down below is specified what transmitters I wanted to map and what receivers I wanted to map. So on the left side here, where it says spotter in parent DE, that's the location of the skimmers on the reverse beacon network. So I selected at the bottom where it says continent, I selected North America. And on the right-hand side of this web page, you can select the location of the transmitters that are active when the map is drawn. So you can see that I selected Europe. So this map plotted all of the European transmitters that were heard at the moment that this map was drawn, all of the active transmitters from Europe that were heard in North America on 80 meters at midnight on this night in January. And you can do this for any combination of bands, any combination of continents that you wish. And also, if you notice all those selections below, instead of selecting a continent, instead of that, you could select CQ zone or ITU zone or a DXCC country, or if you wish, you can specify the call sign of the CW skimmer. For example, you could select W3LPL and look at what my skimmer is hearing and ignore all the other skimmers around the world. And also for the transmitters on the right-hand side, you can specify a particular call sign of a particular transmitter. So this can be either very broad, as it's shown here, with all North America signals heard from Europe on 80 meters. You can select multiple bands too. You can make this map into a real mess by selecting all the bands. So anyway, that's the end of the presentation. I've consumed almost my entire hour and a half, but I'll be happy to take a few questions. Tom, back to you.
Okay, Frank, thanks an awful lot. Dan, K2YW, has a question. Dan, why don't you unmute yourself and ask your question?
I'll try to remember what it was. It was back on the chart with the pie charts that showed the effect of the high-speed stream.
Yeah, the pie charts. That's probably the best part of this whole presentation.
Yeah, I had a little bit of confusion. Maybe I was trying to remember too many things. But you talked about in a prior slide, maybe one or two back, that the real effect of this CME was that the high-speed stream caused a compression against the solar wind.
Yeah. Okay. So I'm sorry I confused you a little bit, Dan. The interaction between these eruptions from the sun and the solar wind is primarily these coronal holes, that what is abbreviated here as CHSS, and notice in the wording here, CHSS interactions with the solar wind. So the curious thing is that these coronal hole streams, they intensify as they travel to Earth, as they interact with the slower solar wind. But these CMEs are massive clouds, and their primary effect is it's just the amount of charged particles that are coming towards the Earth in these huge clouds, rather than the speed of the streams that are coming from coronal holes. So that interaction you're speaking of deals almost exclusively with coronal holes that primarily affect propagation during solar minimum during the last 5 years.
Okay.
Okay, Frank, we have a question from Andrew M. I won't try to butcher his last name, so I'm not sure how it's pronounced. Why don't you go ahead and unmute yourself, Andrew, and ask your question?
Andrew is being shy.
Yeah, it's He's listed as AM. I'm going to unmute you, Andrew. Maybe that'll help. Go ahead and speak up.
Hi,
Well,
thanks. Sorry about that. Um, uh, yeah, so I know that there's been some discussion of dxing and contesting and how that will be affected potentially by the new solar cycle. But I was curious, as someone with a physics background, what ways are there to do, say, for instance, a background observation of, I don't know, maybe the magnetic field strength during either a CME or just at any given time, now that the solar cycle is ramping back up, just to get data on the phenomena themselves and whether any of that could be done with ham radio equipment. Thanks.
Yeah, Andrew, thanks for your question. There is an enormous amount of real-time and retrospective data about the state of the sun, the state of the interplanetary magnetic field, the state of the solar wind, and the state of the ionosphere available on the web. For most hams, the sites of primary interest are the SWPC site, the solar weather site. I don't happen to remember that, but if you just go on Google and just type in SWPC, it'll probably take you to that site. And if you can't figure it out, send me an email and I'll give you the address. So that has a lot of information that's physics based. Another site that's very good is SILSO, SILSO, and it focuses primarily on sunspot activity. So that's another one to go to. And then there are a number of other quite good sites. If you just do a Google search for space weather, it'll bring you to quite a few of them. So you won't have any trouble finding them. And if you do have any trouble, you've got my email address, send me a note and I'll give you some very specific web addresses to go to. Tom, are there any other questions?
Yes, we have a question from Sig. Go ahead, unmute yourself, Sig, and ask your question.
Yeah, just a quick question. I missed the very beginning of your talk because I had a problem here, but I don't think you covered this. What is it that causes the skew path openings, like on 40 meters, where you beam southwest and you get most all of Asia?
Yeah, hi, Sig. Most of you probably don't recognize that voice. I've heard it for the last 60 years. SIG was my first contest QSO after I got my general class license. So SIG and I have known each other for a long time. It was in a seeding party in April 1960. SIG, that's a really good question. Mostly what it's about is that when the propagation path does not exist on the short path, and for example, and I'll just give one of these examples, there are many of them, but one of the very prominent ones is we often lose propagation on the short path between the east coast of the United States and Japan on 40 meters during the night. And the reason for that is that the MUF for signals that are passing through the auroral oval or just south of the auroral oval, the MUF drops below 40 meters. So that doesn't mean that we can't communicate between the East Coast and Japan. It just means that our preferred path, the short path, is not supported because the MUF has dropped. So what does still exist are various scatter modes. And those scatter modes tend to be off of large ocean waves in the equatorial regions. So what you'll wind up pointing to instead of the preferred path, which is short path, is the preferred scatter path, which is generally kind of pointing at New Zealand in that particular case. So Sig, there are lots of other cases, but I can't take the time to go through them all, but that's one of the prominent ones. But the primary thing to think about is that the preferred short path is not available to us because the MUF is too low, but there are various scatter modes that allow the long path or a scatter path to exist. And there's even more interesting of these paths on the very, very long paths, like from the US to, let's say, South Asia at sunrise. But I don't have time to go through all that. We'll talk about that some other time. We've got 60 more years to talk about that, I hope.
They seem to be more prevalent during sunspot highs, though.
Yeah, because the ionization is more intense.
Okay.
We can talk a lot more about that over a beer someday. That'll be a lot more fun. Get somebody from the FRC to invite me to come up there again. I'll be happy to do it. Any other questions?
Yes, Gary, WR3R, go ahead and unmute yourself.
Yeah, thanks. Can you hear me?
Yeah, Gary, go ahead.
Okay. Hi. I just really, it's just a two-part question. I think you said you've seen the auroras twice, Frank. I was
Twice.
wondering when that occurred, and secondly, was there one back around 1970 or 71 that could be seen here?
Well, all I can tell you is the ones that I've seen. There are undoubtedly many more that I haven't seen. But you have to be kind of alert. The time you're most likely to see the aurora is after midnight, and that doesn't mean you can't see it before midnight. But the really spectacular ones are generally after midnight, and you have to be awfully lucky. So generally, in this part of the country, the highest probability of seeing the aurora is in March and April. You remember I showed you those charts that showed when geomagnetic disturbances are most likely. So it's mostly March and April, or September and October after midnight on a cloudless night with no moon. And those things don't happen very often in the mid-Atlantic. I've seen it twice. And one of them was a routine one where the sky simply turned red. So it looked like we were having the typical red sky for sunset, but it was 1 o'clock in the morning. And the other time that I saw it was truly spectacular. It's some of these like some of these movies you see with all kinds of different colors and motion in the sky that seems supernatural, where an effect you were seeing in the northwest sky moments later appears to have moved to the northeast sky. It's just incredible. So those are the two that I experienced. I have no idea if I'll see it again. You have to be very lucky, and you have to be out there after midnight on just the right kind of a night. Tom, any other questions?
No, I believe that's it. So, Frank, if there's any last thing you'd like to say, do it. And then I'm going to turn it over to our PVRC president, Dan, just in case he has anything that he wants to announce. Frank, anything final to say?
Okay, Tom. Well, thanks very much for inviting me to do this, Jim. It was my pleasure to do it. I'm always available to clarify any of this. I realized this was like a fire hose. Probably 100 different people could have gotten PhDs in every one of these topics we discussed, and we covered the whole thing in an hour and a half. So it's not too surprising that it was like a fire hose. Anybody that really wants to cover this in more depth, I tried to be very careful to use the exact correct terminology on each of these phenomena, and you can explore it yourself in further detail by using your friend Google. And you can go everything from popular press all the way to PhD dissertations and everything in between. So good night, everybody.
Okay, it was much appreciated, Frank. Thank you so much. Dan, anything you want to say before I close the meeting?
No, let's keep this just about the presentation, but like everyone else, I really appreciated this. I've seen many of Frank's presentations on related matters, and I always learn something. In spite of the fire hose, Frank, you know, some of that moisture makes it into my mouth and I swallow it. I add a little bit to my general knowledge. So I think this is great. I very much enjoyed this, and I'm sure the rest of the audience did too. Thank you.
Okay, well, thanks, Dan. With that, I'm going to shut the meeting down. I hope everybody has a good evening, and best 73 to you all from PVRC.